Hey everyone, this is Dr. Walker. In this video, we're going to go over the third example from v579 on solenoids and toroids. This example is going to be about a toroid, which is a device that creates an almost uniform magnetic field in some enclosed area. The device consists of a wire that is wrapped around a ring shaped like a donut made of a non-conducting material. You can think of it as a solenoid, but a solenoid is curled into the circular shape like this. So we're trying to find the magnetic field inside this region here, enclosed by the toroid. So we know that we're going to use Ampere's law. Find integral of B dot ds equals mu naught I. We need to choose an Amperian loop. We're going to choose a circular loop. And that's going to take advantage of the symmetry, because if we look at each individual loop and the way that the current is going, for example, if you look at the current here going up and then it's going down behind, if you curl your fingers like this, your thumb is going to point in the direction of the field produced. So each loop produces a field this way, which is along this circle that we chose for the Amperian loop, so that our dot product will vanish and B will be constant along this loop as well. So for the left-hand side of the equation, we're going to get B times 2 pi r, where 2 pi r is the line integral of ds, which is the circumference of the circle of this Amperian loop that has a radius r. And then we need to figure out how much current is enclosed. And this is where, if you're looking at the picture, it might be kind of hard to think about it, because you can see the wire kind of curls like this. But this is where you want to think of it, the current enclosed, as the current penetrating the surface. So if you create a surface here that is bounded by this Amperian loop, then where is the current penetrating it? And you can see it's penetrating always here, right? The current here is going into the page, into the page, into the page. So everywhere the current is going into the page here, it is penetrating that loop. So if the toroid is carrying a current I, then the total current that is penetrating is going to be N times I, right? How many ever loops there are that are penetrating. And now we can solve for the magnetic field, the magnitude of it in this region, distance r from the center within this toroidal shape, mu naught Ni over 2 pi r. So that concludes our examples using Ampere's law to find the magnetic field due to some current distributions that have a high degree of symmetry.